that
Okay.
work?
Hello, everybody. I'm Christine McCormick, chair of the Hershey's Mill Nature Group, and Sherry Kane is the chair of the Technology Committee. And our groups are co-hosting this presentation by Dennis O'Leary called Return to the Moon. Dennis is a NASA ambassador, which means he knows a lot about space and he shares it with people in general. I think there are like 700 NASA ambassadors, and so we're really very lucky to have him here in Hershey's Mill. He's given us a number of talks, and we're happy to have this. This is actually a return engagement because it was so popular when he did it in person. So with that, Dennis, you want to get started?
Okay, welcome everybody. Um, this is a picture of the moon that you're looking at right now. I really urge people to go out when the moon is available and just take a good look at it. It's our closest celestial neighbor, and you don't have to go and buy an expensive telescope to go and look at it. It's right there for everybody. If you happen to have binoculars or a small telescope, you can see things that are really something special. The moon is one of my favorite objects to look at in my telescope, but I don't need it to see things that are up there as well. Um, I just want to mention, though, that if you have a small telescope or even binoculars, don't look at the moon during a full moon because the light is so bright that it could harm your eyes. Um, so when it's a quarter moon or something like that, it's easier to watch because you can see more detail through the contrast. The moon has no light of its own. This is all reflected light, light that's reflected from the light that the sun cast onto the moon that's reflected toward Earth. Okay, so let's see. I want this moon. Okay, so from a distance, like looking at it with your eyes, uh, the moon looks mostly flat. Um, the
They're
darker
showing the moon
areas,
tonight, and these little black.
hello? Um, the moon looks mostly flat. The flatter areas are what we call mare or seas, because when people looked up at the moon before telescopes were made, they looked at it and thought those flat pieces must be where the oceans or seas are located, not realizing that it's a kind of a solid piece of rock. The lighter hills around the outside, this one on the bottom is more visible for you. Those are called the lunar highlands. They're a lighter color and mostly covered by higher craters. The craters are those circular pieces that you see. And since there's no atmosphere on the moon, those are caused by meteorite impacts. Um, the line separating the dark area and the light area, the sunlit portion and the dark area, is called the terminator. Um, but let's get back and start at the beginning. Where did the moon come from? First off, there were several theories or ideas about where it came from. Some thought it was just always there. It started, and when the Earth formed, it was right there. Others thought that perhaps when the sun, when the moon, when the Earth start formed, it was spinning very fast, and a chunk of it just flew out and formed the moon. Um, those theories have pretty much been debunked right now, but I just want to give you an idea. The planets, the rocky planets of our solar system, were formed um, in the same protoplanetary disk that the sun formed in. And there were pieces of rock. And as these pieces of rock collided with one another, the kinetic energy of motion transformed into a heat energy, and that heat melted the rock. Okay, and these rocks would pile upon one another, and these impacts caused the rocks to actually form larger and larger pieces, but the heat was just so intense that these pieces were molten. A thin crust on the outside, but molten rock on the inside. So this is a video of how the moon formed. It starts off in a sky looking very peaceful, but it had a very violent beginning. As the Earth was forming, it was, like I said, it was very hot, and it had a molten core, and it glowed. It was so hot with a thin crust on the outside. An object similar to the Earth, but much smaller, uh, had a glancing blow. Come on, hit it. And the molten debris that was hit, that collected outside and about 11,000 miles away from the Earth didn't fall back. Everything else fell back onto the Earth, but if it was beyond 11,000 miles from the Earth, it formed into these little clumps. And as time went by, a very short amount of time, the moon itself took shape. Okay, this says a month later. It was probably closer to a year later, but that's how it started. And as you can see, the glowing of both objects at the time. Okay, that theory is shared by most scientists now because of the Apollo missions. The materials and data that they retrieved provide evidence for that type of scenario. So let's see what we got. This is the Saturn V rocket that was used for the Apollo missions. Most of this rocket is filled with fuel. There are 5 rockets, motors down at the bottom, and there are multiple layers. When the first section was finished with its fuel, it would drop off and new motors and new fuel would start up and another engine would go. And eventually they would take it all the way up to the moon, at what was left of it after those engines and empty fuel canisters dropped off. The space shuttles that we designed after the Apollo missions were meant for orbiting the Earth and not to travel onto the moon. The furthest the space shuttles got was about 400 miles above the Earth, and that was to repair the Hubble Space Station, the Hubble Space Telescope. Today we have a new system. It's called the Space Launch System, and it's designed to take us to the moon and Mars and who knows where else. This is a picture of the Apollo taking off, the Apollo mission taking off. And this is a picture of the landing craft with 2 astronauts inside of it as they're descending onto this lunar surface. You can see those hilly areas there. Those are the islands. And you can see the flatter pieces. Those are the mare. Just to give you a better idea of what the moon looks like, I'm going to give you a little bit of a moonscape here. Those are the lunar highlands at the top and the mare in the bottom. And that squiggly little line there, that's what's called a lava tube. There are a lot of lava tubes up there. And you can see these little craters. Now, those craters themselves are probably only 50 or so feet across, the smaller ones. But in addition to those, there are boulders and things that you really can't see from this height. This is about 60 miles above the lunar surface. So you really can't see the debris that's actually toward the surface itself. We think that the Mare came when the moon was, the crust of the moon was still thin, and asteroids hit it and crushed right through the thin crust and had molten lava flow out and fill in that basin area so that it looked flat. And these subsequent craters were formed, and that's a lava tube that's been collapsed, that little ridge there. The lava filled in the basin where the asteroid crushed through the lunar crust and filled in. And that's where you see that. So we're going to move on. This is a picture of one of the astronauts on the moon. The spacesuit is designed to protect them from the intense heat and to supply them with oxygen and radio equipment that allows him to communicate with the command module, which is above him, and that would relay signals to Houston, where they were communicating with the astronauts. The backpack has his oxygen, and the suit is lined with small tubes which carry cooling fluid that protects him. The outside area on the moon during the daytime is about 250 degrees Fahrenheit. And at night on the moon, when it's in the dark, it's a minus 250 degrees. All of our missions so far have been conducted during the daytime on the moon. And as longer and longer missions go on, we'll be having to concern ourselves with night as well. The daytime on the moon lasts for about 14 days in any particular spot. And night as well lasts for 14 days, Earth days. These are some of the things that they brought down onto the moon. The object in front of the astronaut is called a seismometer. On Earth, they measure earthquakes. On the moon, it measures moonquakes. It was able to detect when meteorites struck the moon. It also detected they crashed things into the moon to get readings. And from those seismometers, they were able to tell what's the inside of the moon structure. In between you can also see the flag in the background, the American flag, and between the flag and the seismometer is an object called the Lunar Ranging Retroreflector. That's it's a big word for a mirror. And what that does is if we shine a laser beam at it from Earth, we can measure the time it takes for the beam to go up to the moon and return back to Earth. And it takes about less than 3 seconds for that to happen. And by doing that and knowing precisely the speed of light, we can tell how far away the moon is at any given time. The moon is actually moving slowly away from us. I say slowly, it's about 4 centimeters every year or something like that. It's not a lot, but it's moving very slowly away from us. One of the rocks that they brought back from the moon is this. This is called basalt. It's a mineral like we have on Earth. This is a volcanic type of mineral. You can find it in Hawaii or Iceland, any place that they have volcanic activity. So this is the basalt. This is what you would see in the darker mare. this is a rocky material called breccia. And when a meteorite would hit the moon, where it would strike uh, became very, very hot. As I mentioned, the kinetic energy turns into heat energy, and any soil that was there, any kind of rocks that were there that was cracked open by this meteorite impact, suddenly melted together. And this is just an amalgamation of different types of minerals all combined together because of that heat energy. The lunar soil or regolith is very powdery. It's like a talcum powder type of substance. Um, it's very fine. It's electrostatically charged because of the the solar wind, the light that comes in from the sun, and the solar wind, the solar energy that comes in from the sun, gives an electric charge to it. So the astronauts' spacesuits got clingy with this lunar regolith. Um, Additionally, they had to be very careful with it uh, because this is also, it's not like our talcum powder in a sense that there's no, this is very brittle. It's more of a silica type of material, and it's very brittle and glass-like. So the edges of it are very sharp. A Chinese rover was up on the moon a couple of years ago, and they made a big deal about having it roll out and so forth and so on. And after about 2 weeks, it just stopped because this lunar dust got into its gears and ground them to a halt. The astronauts have to be very careful not to get this in their lungs because this could just rip their lungs apart. It's very dangerous. This is one of the astronauts collecting rocks. All of the astronaut teams collected rocks or soil and brought them back to Earth. Now, the last mission, Apollo 17, sent a geologist up to find rocks of importance, things that would really tell us something, and not just rocks that would happen to be haphazardly strewn around the moon. This is what he brought back. This is a mineral called anorthosite. It's a calcium feldspar kind of mineral. We have it here on Earth. It's a very low density, which means it rises to the top. And it's something, this is the rock that really explained how the moon formed, okay? This is just a kind of an aside right now. These are images of these landing sites for the different Apollo missions. And you can see the discarded landing craft that's there. And you can also see the footprints of Apollo 11 and 12 on the trails there as they walked around. And on number 14, they had a wagon that they used, and 15, 16, and 17 had a rover that they drove around. So they had a longer range that they could check out the different things. So what did we learn from these trips? This is one of the things that we learned. This is the far side of the moon. We can't see this from Earth. Only the near side of the moon faces us, and the far side never does. We'll explain that a little while later. But the far side looks a lot different. There aren't many mare on it, and it just looks so much more cratered than the front side. And that's because I believe the heat of the Earth, as the moon was still so close to us, caused the heat on that one side to be much hotter on the moon. And when that got hit, the asteroids were able to puncture through the surface of the near side, where on the far side, it was more thick at the time that was happening. And that was why these got cratered more, and mare happened on the front side, or on the near side. The reason we think that the moon formed the way the movie showed was because it differentiated, or it formed the same way the Earth did. The heavier materials like iron and nickel floated down to the bottom, to the core of the Earth. The other areas, the lighter kinds of materials like the northernite and different silica and calcium type of minerals, floated more to the top. And in between, you have other different levels of the different minerals that are the densities of the different minerals. So that is what kind of convinced the scientists that this is why the Earth and the moon formed. They formed the same way, and they differentiated it out the same way. And that's what scientists believe is the way it happened. These are moon samples that were opened in March of 2022, 50 years after they were collected. We still have hundreds of pounds of samples still in a vault, a cryogenic vault in the Johnson Space Center in Houston. When they brought these samples back, they purposely used a small sampling of them to get some information about the moon, but they held back a lot of rocks and a lot of soil because they knew that in the future we would have better techniques and better equipment to use to analyze these things. And as it turns out, they were pretty correct on that. These things are still being studied through colleges and universities throughout the United States and the world. So what else do we know about the moon? It has less gravity than the Earth. If you weighed 120 pounds on the Earth, you'd weigh only 20 on the moon. It has some water in the rocks and in the soil, and the craters at the polar regions have a lot of water in the form of ice. If a comet were to hit the moon, the ice, because of the less gravity, would flow around the entire moon. And the polar regions where any ice would fall in the polar regions, in the craters those are regions where the sunlight never hits. They're so deep that the sunlight never gets to the bottom of those craters. So that ice would stay in there. And over the billions of years that the moon's been formed, there's a lot of ice. We know that there's a lot of ice in those craters on the different poles of the moon. So let's see what else. How big is it? Why does it seem to change shape? What makes it super? Why do we only see one side? What causes the tides? And can you see the face on the moon? So the Earth and the moon are both spheres. The space inside a sphere is called its volume. So if we wanted to know the volume of the Earth as opposed to the volume of the moon, we would just have to get our old formula from high school math, and the volume is 4/3 pi r cubed. So if we divide the volume of the Earth by the volume of the moon, we can tell how much larger the moon is compared to the moon. And I did this math for you. And it turns out that the moon is 49 times larger than the moon. So let's look at how this works. When I go to schools, what I do with this activity is I would bring in a can of Play-Doh, and I would ask the students to make 50 balls of about the same size. And then we would take one ball that was representative of the group and now crush the other 49 into one big ball. So we have a relative size of the Earth and the moon. Now the circumference of the Earth at the equator is about 24,000 miles. The distance to the moon is about 240,000 miles. So if you divide 24,000 into 240,000, you get 10. So if we had a string large enough to wrap around the center of the Earth, the circumference of the Earth 10 times, we could then stretch it out and reach the moon. So we have the students stretch this cord all the way out, and it comes out to about 6 feet at this scale. So there they have the relative size and distance of the Earth and the moon. So you can try that with your grandchildren. Okay, let's see. Can we hear this?
Hi, my name is Emily Morgan, and I'm the author of Next Time You See the Moon from NSTA Kids. And I'd like to share a simple activity with you that can help you understand why the moon looks different at different times throughout the month. Why sometimes it looks like a banana, and other times it looks like half of a circle, and other times it looks like a big round ball. Well, to do this activity, you only need 4 simple things. You need a lamp with the shade removed, a white foam ball, a pencil, and a dark room. The darker the room, the better. Now in this model, the lamp is going to represent the sun, and of course the white foam ball is going to represent the moon, and your head is going to represent the Earth. So let me show you how this works. We know that the moon orbits the Earth. So in this model, I'm going to get the moon, the foam ball, to orbit the Earth, my head. Notice that no matter where the moon is in its orbit, half of it is always lit up by the sun. But when the moon is in this position, I can't see any of the lighted side of the moon from Earth, my head. From this angle, you can see what I am seeing from Earth. We call this new moon. When it's new moon, we look up at the sky and we can't see the moon. It's there, but the side that's reflecting sunlight is away from us. Now, as I slowly make the moon orbit to my left, I can begin to see a tiny sliver of that lighted side. We call that a crescent moon. As the moon keeps orbiting, we can see more and more of that lighted side. We see half of the lighted half, which is a quarter moon. In this case, a first quarter moon. As we keep orbiting, we see almost the whole lighted side. We call that a gibbous moon. Then, when we can see the entire lighted half of the moon, that's a full moon. As the moon continues in its orbit, we begin to see less and less of that lighted side. We're back to a gibbous moon, but this time the light is on the opposite side. Then another quarter moon, last quarter moon to be exact. Another crescent. And finally back to new moon. And the cycle begins again.
Okay. Yeah. Well, this is certainly correct. Anytime that I've done this in a school, it's never dark enough. The only time that I've been able to do this and have it work properly was inside a planetarium dome. So that's why I do this on video now, because it's just impossible to get it dark enough in a room. Also, these are the phases here, and I just want to point out, during a new moon, the moon itself is directly overhead at noon. By the first quarter, it's directly overhead at about 6 o'clock at night, midnight at a full moon, and 6 a.m. for third quarter moon. So if you're looking for where it is on a particular thing, midnight is where the full moon is. Now, these are standard times, not daylight savings times. Okay. Oops, let me go back. Yeah. Okay. Now, if you pick out any particular point on the moon, you'll see that it does take 14 days for it to change from day to night. 14 Earth days, only one moon day. Okay, that's enough. Okay, we right now are in the period of time when we're getting super moons. Last month we had one. Next month we're going to have one, and we'll have another one after that. They come in cycles of 3. A supermoon just means that the moon is closer to the Earth than it is in other parts of its orbit. It's also, when it's furthest away, it's at what we call apogee. That's when it's most small in our view. Uh, Most of the time, the other 6 months, it just looks normal to us. And the difference that you really can't tell a difference because without a light meter or some sort of equipment, the difference to you will not be really something that you would notice. It's about 11% difference in size, but it's really hard for you to make that distinction uh, because it's been, like 6 months since it happened before. So, but that's the only thing. The news media seem to make a big deal about it, but it's just because the moon is closer to us for 3 months than it's normal for, in its orbit around the Earth. And then it gets further away and then it gets smaller in our view. Now we only see one side of the moon due to synchronous rotation. This is a little iffy, a little difficult to explain. I've done it with a tennis ball, but this video shows it a lot better.
What if the moon merely rotated? We here on Earth would be able to look up and see all sides of the moon, right? Of course, Earth spins too, but to simplify our discussions, let's hold it still for now. Also, let's add a yellow line so to make the rotation of the moon more apparent. Note that as the moon rotates, the line goes from vertical to horizontal to vertical to horizontal and so forth. That means it's rotating. What if the moon didn't rotate and it only revolved around us like this? We'd still be able to see all sides of the moon, right? What if the moon both rotated and revolved? How about like this? Look carefully and you'll see that, yes, we still get to have a 360-degree view of the moon. No hidden sides. But what if the moon rotated just as fast as it revolved? Like this. Ooh, check this out. The moon is rotating, right? Look at the line, if you don't believe me. Vertical, horizontal, right? But it's rotating at a rate that matches the revolution. Just so that only one side of the moon ever faces Earth. And that's exactly the situation we find ourselves in today. The only side we ever see, we call the near side. The side we don't ever see, we call the far side. Actually, the first time we ever saw the far side was from photographs sent by a Russian lunar spacecraft in 1959. But no human ever saw the far side directly until the Apollo 8 mission in 1968. But why don't we, here on Earth, ever see the far side? Why does the moon spin exactly as fast as it revolves? Good question. I mean, very good question. We could spend weeks studying this one question. But I'll just give you the quick explanation. For starters, let me tell you, it's no coincidence. Earth's gravity gets weaker with increasing distance, right? Yeah, but over the distance of a few meters or even kilometers, this difference is not that much. The Earth's pull of gravity on your head is, for all intents and purposes, the same as it is on your feet. The moon, however, is thousands of kilometers wide. So the near side of the moon experiences a significantly stronger gravitational field from Earth than does the far side. What this means is that the moon's center of gravity relative to Earth is not the same as its center of mass. Center of gravity? Huh? The moon's center of gravity is the point upon which all of Earth's gravity appears to act. You could scrunch the moon to the single point, and gravitationally speaking, there'd be no difference. If Earth's gravity acted uniformly across the moon, the center of gravity would be the same as the moon's center of mass, which is the average point of the mass of all the atoms within the moon. Yeah? But because Earth's gravity is stronger on the near side of the moon's center of gravity is shifted toward the Earth, like this. Now, the moon's center of gravity can be considered to be the point upon which the Earth tugs. If the moon rotated a bit faster or slower, the center of gravity would be lifted away from the Earth. And you know what happens to things lifted away from the Earth? That's right, they're pulled back down. The Earth would apply what we call a torque, which would align the moon right back to a position where the center of gravity is directly below the center of mass. Kind of like this. This is what prevents the moon from rotating any faster or slower than it does. The moon can only rotate so fast because Earth won't let it do otherwise. As a consequence, the moon rotates only once for every revolution, and only one side of the moon ever faces us. The differences in Earth's gravity between the near and far side of the moon has other effects as well. For example, it has the effect of stretching the moon into a somewhat oblong shape. This happens because the force of gravity isn't applied uniformly. Earth's uneven gravity acting on the moon causes an oblongish deformation. Remarkably, the moon has the same effect on Earth. This is most noticeable with the Earth's oceans, which are relatively easy to stretch. As the Earth rotates beneath this oblong shape, the sea level goes up and down. As we pass under each bulge, we experience high tide, twice a day because there are two bulges. The two low tides are when we pass under the narrow regions of this oblong distortion. This oblong distortion tends to hold the oceans still relative to the moon. So there's actually a bit of friction between the ocean floor and the water as the Earth rotates. This friction, combined with a small torque on us by the moon, is slowing our rate of spin. As I said earlier, back in the time of the dinosaurs, a day was about 19 hours long. In a billion years or so, a day will slow down to about 46 hours. At that point, only one face of the Earth will face the moon, much like only one face of the moon now faces the Earth. By the time this happens, the moon will be much farther away because of the conservation of angular momentum, which we haven't talked about. But like a fast-spinning ice skater, slowing down needs to throw her arms outward. The moon, slowing down Earth, can only do so by moving itself outward. Then the Earth and the moon will be completely locked in their dance around each other. Right now, The Earth is kind of shy and always turning away from the moon's constant gaze. But when Earth finally returns that constant gaze, when we're finally completely locked together, the moon will appear at a single location in our sky, day and night. People on opposite side of Earth won't ever get to see the moon unless they go on vacation to the moon view side of our planet, where I'm sure real estate prices will be higher, along with the sea level, in a billion years from now.
Okay, just two things about this. The tide section doesn't really explain too much about the tide on the non-moon facing side of the Earth. There's two reasons for it, and one had to do with the greater pull of the moon as it's the ocean is nearer to the moon. There's a strong pull of the moon on that for that tide, and the Earth itself is a big rock. So the mass of the Earth is also pulled by the moon, but not to the same extent as the fluid ocean at the top of it. The bottom piece is actually being pulled away from the rock of the Earth because it's not getting as much of a pull of gravity from the moon. That's part of it. The other part is that the Earth is spinning. And if you've ever been on an amusement park ride where you're spinning around, you get pulled away, and that's called the centrifugal force. And that's what's actually pulling or helping the moon to pull away that bottom tide. So it's a combination of the less pulled by the gravity than the Earth itself has, and also that centrifugal force as it spins. Okay. Now we're into the next phase, the Artemis program. Artemis is in Greek mythology, the twin sister of Apollo. And during the Apollo mission, all of the astronauts were men. And now we have women in our Corps as well. So the odds are that the first person who's going to step off the Artemis program onto the moon will be a woman, which is fine. So here we go. This is the NASA's Space Launch System. It's the largest rocket and payload that has ever gone up into space. And it's the backbone of our human space exploration program into deep space. And it's also being supplemented. NASA is also supplementing other private companies such as SpaceX, which is also taking rockets into space. And we are going to be relying on these commercial assets as well as the Space Launch System to get our astronauts safely onto the moon. So good shout out to them. This is a picture of the Orion space capsule. This is where the astronauts would be on their way to the moon. The capsule itself is much larger than the Apollo astronauts were able to get in. And there'll be room for 4 astronauts on this. And we'll continue. This will bring them to the moon or to an outpost on the moon and then return them safely to Earth. This was a map basically of Artemis 1. This has already been done. And this happened in November and December of 2022. We sent a spacecraft with no people in it just to see if it would work. And we sent it around the moon several times and back to Earth. The Orion capsule landed safely on Earth, and they've been going over it to make sure of what went wrong, what could be done better, where the flaws might have been, and so forth. It didn't have too many flaws getting the spacecraft up, excuse me, up and back. But there might have been different issues that could have been done better. And now the spacecraft itself, the Orion spacecraft, is being upgraded, and the new Space Launch System is getting ready itself. Artemis 2 will be the next project that will take place no earlier than September of 2025. I tend to doubt that that date is concrete. I think it's maybe a year past that. They were having difficulty with spacesuits, as did SpaceX and whatever else is up there now. But they wanted to make sure that the spacesuits that were that the astronauts were going to be in on this trip were going to be adequate, and they had a delay with that. And as I said, they were still refitting the Orion capsule. So I don't think this is going to go up when it's supposedly scheduled, but it should go up within the next year or so. So anyway, that's the next project for Artemis. This is a representative crew. These are astronauts, but whether or not these are the ones going to go is anybody's guess, because we don't know when it's going to go. The next phase of the Artemis program is setting up a space station around the moon. This is going to be orbiting the moon. It's called Gateway. The astronauts on the Orion spacecraft would dock here. They would transfer to a lunar landing facility. It's a rocket that right now we believe SpaceX program will be designing, and it's going to be a landing craft. It's going to go down to the moon, and it will land there, and the top section will bring the astronauts back when they're ready to come back. The bottom section will be left onto the moon and eventually tipped over and turned into a living facility, as I'll show you later. This gateway is going to be used as a docking facility for supplies to go to the moon and for the astronauts, and it will be expanded into a regular space station, much like the International Space Station is. We're also going to use this area of the sky or off the moon to use it as a fuel dump, where we'll be able to refuel different spacecraft as they get near it. This is the Artemis 3 program. This will be no later than September of 2026. And again, I doubt it, but you didn't hear that from me. It's going to go around the Earth, orbit around the Earth. Then it's going to get into the Gateway station, and then a craft will land on the moon. When they're done doing what they're doing, they're going to come back to the Gateway and return on the Orion spacecraft, which will be docked there for them. Now, how we're going to the moon. This is a little NASA propaganda for you.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. and a launch abort system with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there was no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit, and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
Okay, that's Artemis 1, 2, and 3. What is happening after Artemis 3? And first off, Artemis 3 is basically seeing if we can launch people back onto the moon and bring them home safely again. So we're starting to put people back on the moon. We want to start to colonize the moon, put colonies of people on. And the reason is that's what's going to happen as we get to Mars. So we want to practice what's going to happen in Mars while we're on the moon, only 3 days away, and we can get people back very quickly if something happens bad. The moon is 2 years away. There's nothing we can do. And these people are going to be there. We got to try to make sure everything is set up properly for them ahead of time. This shows one of the things that the first group of people are going to be trying to find is water. We already have commercial enterprises that have robotics right now that once they get rolling, they'll be launching to the moon before people get there. And they're going to be looking for signs of water, where we can find it and how we can get it useful. They want to try to have a storage of water on the moon before humans actually wind up getting there. With water, we can separate H2O into hydrogen and oxygen. The oxygen can be used for breathing. The hydrogen can be used for fuel, as well as the oxygen can be used for fuel. Or we can just use it for water. Water can be used for construction materials. It can be used for plants. It can be used for drinking. There's a lot of uses for water in general. So we want to be able to extract the water from the rocks, the craters, the soil, and there are many different international and commercial entities right now looking for ways that they can get that done. This is an artist's rendition of what a lunar colony might look like. As you can see off in the distance there's behind the car, behind the rover, is a mound of dirt packed on top of this cylinder. Well, that cylinder was one of those landing craft that I told you was going to land and remain on the moon and then get toppled over. That's what's going to happen. And the soil from the moon is going to be mixed with water and a resin type material to form a concrete type material that they can cover those things with. One of the problems with the moon is that it's exposed all the time, or during the daylight hours anyway, or the daylight days, it's exposed to the solar wind, which carries a lot of solar radiation. It's things that their spacesuits will not protect them from. So they have to have some sort of a place to go to be protected from the radiation. It's going to be a lot of solar batteries and things like that up there, a solar array of panels. And they're also working to perfect some of those as well. And plants. We're going to be trying to grow our own plants up there, hopefully using soil from the moon if we are able to get that done. There's no real chance that we're going to be bringing soil from the Earth to the moon. It's just too heavy and too expensive. A pound of something being launched into space costs about $10,000. So there's not a lot of room in a spacecraft to take soil up. So we may either do this, grow plants hydroponically using just water and minerals, or we may be able to somehow use the regolith and get that into a soil for our plants. Gateway, as I said, is going to be expanded. And NASA's mission really is to expand the lunar expedition for preparing to go to Mars. Mars is something for the 2030s. It's not something that we're planning to do right now, but this is, again, the practice drill to get that done. Other commercial areas we'll be looking to get extract minerals or like gold or titanium, things like that, which are up on the moon. They might want to try to mine those on the moon without the restrictions that we have to worry about here on Earth. And there's also helium-3. On Earth, we have helium, but it's helium-4. That's what we have here. There's a very tiny, tiny bit of helium-3 on Earth. It's caused by the solar wind interacting with hydrogen on the moon causes helium-3 to be produced up there. If we had helium-3 and we fused it like a fusion bomb, but not a bomb, it's a fusion of deuterium, which is we have here on Earth plenty of, and helium-3, which we don't have, we would wind up getting a normal helium atom, helium-4, and we would have a proton, which is not radioactive, and we would get a lot of energy from that fusion. There'd be no radioactivity involved. It would just be pure energy, a proton, and a helium atom. So this could help solve the Earth's energy supply problem for thousands of years. Just this, if we were able to, in one way, mine this on the moon and get it back to Earth, and then start some process where we could actually do this fusion. None of that has been taken into account yet, but private companies have started looking into the possibility that they could do that. As I said, in addition to water and helium-3, there's titanium, gold, silver, copper, and a lot of rare earth minerals that are up on the moon. And commercial enterprises are already taking steps to tap these sources of wealth that are up there on what some consider our 8th continent, the moon. Okay, and let's take a look at the moon. This is the lunar highlands. Okay. This is some of the lunar highlands that are up there. And I just want to just picture yourself up on the moon for a mission, 3 months, a year, whatever it might be. You've been up on this rock with a select group of people, and you're returning now. You're looking at the lunar highlands probably for the last time in your life. And you're looking at the darkness of space. And what's the most impressive thing that you'll be able to see on your return? Earthrise. This is what all of the astronauts so far from the Apollo program have seen. And we're hoping that the new astronauts on the Artemis program will be seeing it as well. It's a beautiful sight in the sky. Okay. Now, can you see, when you're looking up at the moon, most of these things you'll be able to see just with your own eyes. I just want to go over them quickly. This is the lunar X and the lunar V. You can see them up there. This is just the light reflected off the tops of different craters to form these images. The lunar X and the lunar V happen maybe they last for about 4 hours, and they come up perhaps every couple of months. So it's a very rare sight to see. But I've seen them. Several of the people in Hershey's Mill have seen them as well, if they were at my telescope that night. This is kind of fuzzy picture of the moon, but this is the picture of, we're going to show you the picture of the woman's face on the moon. Here she is. You can see her hair, her eyeball, eye socket, her mouth. Can you see her? Okay, I'll try to go back. And
Dennis, that's not the most flattering view of a woman.
no, but we do the best we can. Okay, here's the rabbit. And here he is. Okay. And probably the easiest to spot is the basketball player. Oops. There's the basketball player. Can you see his ears?
Yeah, those two are nice.
Yeah. Okay. Questions?
If anybody has any questions or comments, just unmute yourself. And Dennis is happy to talk to you.
Hey, Dennis, this is George. I was just curious when you were talking about how the earth is pulled and the oceans were pulled. Is that what affects the tectonic plates? Is that how we get earthquakes?
No, that it's not that strong of a pull. No, the tectonic plates are from internal.
Oh, okay.
Okay.
Well, the water shifting doesn't have any effect on the tectonic plates?
It has a tiny effect, not any kind of real effect. It has, the tectonic plates are really the motion of the magma underneath pushing up and pushing down.
Okay.
I have two questions, if I may. One is,
I know where you live.
I know, and I know where your telescope is. If we allow companies to go to the moon to excavate and mine minerals,
Yeah.
isn't that going to ruin isn't that going to ruin things at all?
First off, there's an UN law, United Nations law that everybody's been signed a signature of, and any activity of a non-governmental agency has to be linked to a government. So there have to be government regulations involved to permit any kind of excavation of the moon at all, any kind of drilling or mining. So the government itself would be required to regulate that.
Like we trust them.
Yeah, right. Can we trust them? Right.
Don't ask me that. Okay, that was one.
Yeah, the other question is, with all the different countries coming to the moon, you said there are regulations, international law.
Yeah.
Didn't I hear something about the Russians are trying to get something on the moon now to use as a weapon?
Right now, the Chinese and the Russians. The Chinese, I think, we're going to the South Pole of the moon for a number of different reasons. The Chinese seem to be more concerned about the far side of the moon. And I think the Russians, I don't quite know what they're doing, but I know that they have an intent to get back there. But so far, they've only done robotic stuff. I don't know about humans up there from the Russian group. But I know the Chinese are.
Dennis, Rich Sheckman, I have a question. You were talking about the evolution of the moon. I was wondering why, with the distance between the moon and the Earth, why the moon got hit with more asteroids to make those craters than the Earth did. Do you understand what I'm saying? Oh, you're muted.
Dennis, you're muted. I had to mute everyone because there was so much background noise coming from someone. So, Dennis, please unmute yourself. I apologize. I meant to come on and tell you that. And if you're not asking a question actively, please do mute yourself.
Do I need to repeat my question, Dennis? I think you're still muted.
Yeah, you're still muted, Dennis. Give him a second. He'll find it.
There you go.
Okay.
Okay.
I'll repeat my question. With the, as you mentioned, with the evolution of the moon and the evolution of Earth, they have a lot of craters, and you indicated that they got hit with a lot of asteroids.
Yeah.
Why did they get hit more than the Earth did?
The Earth got hit with more.
Oh, they did.
Yes. Our atmosphere, and when we got an atmosphere, and the weathering that we have over the billions of years have eliminated the evidence of most of those. We still have a few meteor strikes and things like that, but for the most part, the weathering and the evolution of the Earth with its atmosphere have reduced or eliminated the evidence of that. The moon has no atmosphere and it's got no weathering, and they just remain there. Okay.
Thank you. Thank you. I'm going to mute again.
Okay. Anybody else? Okay. Well, I hope you enjoyed it as much as I did.
Thank you very much, Dennis.
I loved it.
Okay, you're welcome.
Thank you, Dennis. That was great.
Yeah, thanks so
Okay.
much, Dennis. We appreciate you coming on and doing it again.
Okay.
Thank you.
Okay.